part of Chapter 17, Sections 17.1 and 17.2. I'm going to go through 17.1 pretty quickly because it's the common ion effect. I'm going to show you where the only difference between the common ion and equilibrium stuff that we've done before exists. It's actually pretty easy. So the first part of the 17.1 is actually super easy. So take a look at this. Consider the fact that we have a solution in acetic acid. Acetic acid, you guys know, as HC2H3O2, and on the other side, a very little bit we get is the hydronium ion, which is the acid part, and acetate. If we have acetate ion is added to the solution, as in there's already acetate a little bit in the solution, but we add more in the form of sodium acetate, like this, then you see what happens. So, okay. Then I was getting ahead of myself. So if the acetate ion is added to the solution, the Chatelier's principle says that the equilibrium will shift to the left. That means that if I'm adding this, okay, that if I'm increasing the concentration of the acetate ion, that will push the equilibrium to the left. It will decrease the amount of acid because these two will come together. These two will come together to form more of the reactants, so we'll form more water and we'll form more acetic acid. So those two things, the concentrations of, well, we'll form more water. The concentration doesn't go up, but the concentration of acid does go up. Okay, so take a look at what's happening here. So it says the common ion effect, the extent of ionization of a weak electrolyte, which means weak acid, is decreased by adding the solution to a strong electrolyte that has an ion in common with the weak electrolyte. That's really just kind of confusing for saying that if we have, calculate the fluoride ion, okay, we're going to take a quick look at this, but we're going to do sample problems, so I'm not going to get in depth as to what's going on. You guys know that if I have HF, it splits up into H plus and F minus, and then what I have for the K for that would be products over reactants, concentration of H plus, F minus, all over concentration of HF. Okay, there's nothing new there. Okay, and it looks like the Ka for this equals 6.8 times 10 to the negative fourth. So notice that I have basically the same thing here. The only thing I did was they put the hydronium ion in here for just the hydrogen ion. So let's continue on and take a look at what it looks like. If we do our ice initial change in equilibrium, the only difference is that this would have been a 0 for initial, but now it's at 0.1. Why is it at 0.1? Because they added 0.1 molar HCl to the solution before in the initial. So the only difference is that this is no longer a 0 because there's something else that's common here rather than 0.1. Okay, good. So let's keep going. Notice what happens here is my change is a minus x, plus x, and plus x. So what we get is just like another term like we do on the left-hand side. The left-hand side has the weak acid here, the HF, and we minus x. And remember our 5% rule? 5% rule says that we can get rid of this x here, and we can get rid of this x here also because of the 5% rule. If you don't remember that, you'll see that in the sample problems. Okay, so we just start a little bit different, and then x gets solved like this. This is all just algebra. That's all this is, and I'm going to keep moving through it pretty quickly. So the common ion effect basically says that the pH change from, this is concentration F minus, the change from the concentration at F minus is almost non-existent at all. This should be 0.1. I'm not sure why it's not. But notice that when I add 0.0014 to this, it might as well be that. Okay, so in other words, it didn't change hardly at all. Okay, that's the common ion effect, and I will go over an example problem with you on that. Now let's get into buffers. Buffers are very similar to common ion. It's a very specific common ion, and in a way that helps the pH of whatever solution you have resistant to pH changes by adding acids and bases. That's all buffer is. Okay, you know what a buffer is from before, but here's the actual theory behind it. So here's what I'm going to do. I'm going to stop here so that you can get some info from the common ion, and then I'm going to pick up again with another screencast about buffers.